graph first. Now, last time you have learned what is the graph, right? You have drawn all the diagram and so on. So, if we only say graph, it means that it has two ways relation, undirected. Okay? So, for this one, if let's say the graph like this, if I only want to show using a line instead of the arrow, so I can join this one with a straight line like this. So we can draw this graph becomes roughly it will become like this. Okay, if you follow the two ways relation here, replace it with a line, so you will see that it will roughly become the undirected graph like this. So meaning that here the line here will show a two ways relation. So this is another term that you have learned, symmetric relation, right? Still remember symmetric? Two ways relation, right? Okay, so this is the one that show in the graph here. Okay, now we want to see what is the path, simple path, and then not simple path and so on. So look at this path from vertex A to B. Let's say we have the label here, A, this one is A, and then you have B, C, D, E, F. So let's say we label this graph like this. Then from vertex A to D, we can have a path of A, B, and D. This one we call it as a simple path because there is no vertex that we repeat. You go through once for each of them. Okay? But if let's say I go through like this, A, B, D, and then C, B, D. So in that case, the B and D I already go through twice, right? Then the path like this will be not a simple path anymore. Okay? So we can just give the simple path example from A to D. You can just write it as A, B, D. And then if it is not simple from A to D also, then you can write it as A, B, D, C, B, D. So we go through the B and D for twice. Right? So it is not simple path anymore. Then we go to the cycle. If you look at the graph here, which one do you think that it is a cycle? Any cycle here? Yeah, B, C, D, then go back to B, right? So this one will form a cycle, isn't it? So we can write here, example, you have a simple cycle with B, C, D, B. Okay. Now the term that we use for a cycle here is acyclic. Acyclic means that in our graph we don't have a cycle. Acyclic means no cycle. Okay. So example for this, there is a cycle A, B, C, A, right? So we will say that this is not a cycle. If there is a cycle in the graph, then it is not a cyclic. Okay, a cyclic means no cycle. Then for this one, is it a cyclic? This is a cyclic, right? Because they have no cycle in this graph. So this is to introduce the term acyclic. What is the meaning? And another one we need to know in a graph is connected. So this one is straightforward. You should know what is connected already. That means all the vertices are connect to each other. So this is a meaning of connected. For example, this one, the graph here, AB and CD are not connected. So this one we will say that the graph is not connected. And here you have A, B, C, D, E. All the vertices connect to each other. So we will say that this graph is a connected graph. Okay. These two definition is for us to define the undirected tree. Okay. If it is undirected tree, we must fulfill these two, which is acyclic and connected. Then you will say that it is undirected tree, meaning that all the vertices must be connected. Okay. So now the undirected tree here, you can give the example like this. All these are the vertices. Okay, we don't label it only. So you have the vertices here. All the vertices are connected. So this one, do you think that it is a tree or not? This one, is it a tree?
Undirected.
Huh? Is it undirected tree? Can it fulfill acyclic and connected? Yes or no? Yes, right? So if you find that the graph given is connected and acyclic, that means you can say that this is a tree. Okay? How about the diagram at the right? Is this two graph a tree? Now, what is the reason you say this is not a tree? This one is not
Acyclic.
Yes. This is not acyclic, and this one is
Not connected.
not connected. So these two reasons cause this is not a tree. So after you have known these two, now we go to the theorem again to define these two again, acyclic and connected. So they say that a graph is a tree if and only if the graph is acyclic. Originally the graph is acyclic, means that no cycle, so it is a tree, and it will become not acyclic if you add in one edge to the graph. For example, if we have this, you see without the dotted line here, the graph is acyclic, isn't it? No cycle, right? But when you add in the dotted line, this becomes not acyclic. So the graph original is a tree, but after you add in one more edge, it becomes not a tree. So this is how we define acyclic again. And the second theorem here says that a graph original is a tree because it is connected. But if let's say you remove one of the edge, it becomes not connected. So, example, this one. The dotted line originally is in the graph, so it is connected, right? But after you remove this dotted line, it becomes not connected anymore. So this is how we define when it is a tree with the condition acyclic and connected. Okay? So one is, it is acyclic, you add in, becomes not acyclic. One is connected, when you remove it, it becomes not connected. Okay, so this is the theorem just now. So this one you can just write an edge added then it becomes not acyclic. You add in, become not this one is an edge remove. It becomes not connected. After we know what is the undirected graph here, how do we define a tree for undirected graph? Now we will look at a graph with this condition. This one. What is spanning tree? Now, spanning tree is actually a subgraph from the graph we have with all the vertices connected and no cycle. So we follow the definition just now. We must make sure that all the vertices we have must be connected and there must have no cycle inside the graph that we have. So let's say you are given a graph like this. This is a graph. Undirected graph, right? So if let's say we want to determine this becomes a tree, how should we do? We need to make sure that there have no cycle. We need to make sure that all the vertices must be connected, right? So how do we want to remove some of the edges here in order that we will get this becomes undirected tree, so that it can fulfill the two definitions just now. Okay, so here are all the vertices. These are all the vertices. Which one we need to remove? Let's say I label it A, B, C, D, E, and F. Which edges we need to remove in order that we can get this undirected tree?
BD,
Which one?
the edge from B to D.
B to D.
Oh,
This one is two edges already, right?
yeah.
Can we remove one by one? Okay, one more here. Okay, this is undirected graph. Okay, so we will remove let's say you remove BD, right? Then it becomes like this, isn't it? Is this the tree? Is this a tree? No? What else we need to remove? This one, right? We need to remove this, right? Okay, so some more is this one we need to remove also. And this is one of the undirected tree you can have, which is here is A, here is B, and then this one is the D, this one is F, this one is E. Where is C? You still have here. What you removed just now is BC and CD and also EF, right? You remove the three edges just now and remain this to get the definition of a cyclic and connected for all the vertices. Is there any other way to get an undirected tree besides removing these three edges?
A to C and A to D.
A to C and
A to D.
A to D. Let's see the graph. So here is A, B, C, F, E, D. Remove AC, remove AD. So this is another possible tree, right? Any more?
Remove AC, CD, and CF.
AC, CD, and CF. Okay, so we have A, B, C, D, E, and F. All these. So we remove A, C, C, D, and CF. What do you notice here? How many edges we need to remove every time in order to get undirected tree?
3.
3 edges, right? Now, I believe you still can find other spanning tree where you remove other 3 edges. Correct? Okay? You can think of the different ways by removing 3 of the edges here in order to get it is a cyclic and all the vertices are connected. Okay? So this type of tree, we call it as a spanning tree. Meaning that the original graph is not a cyclic, and by removing the edges, we will change it becomes a cyclic and connected. So this undirected tree, we call it as a spanning tree. Understand? Okay. So we have many different ways to get the spanning tree. So done already this one? Done. You can draw some others spanning tree by your own. Okay. Now, how do we want to build a spanning tree by using algorithm? Instead of we do it manually, if the graph given to you is a simple graph, then no problem. You can just remove the edges one by one to get the undirected tree. But if let's say the graph given is a complicated graph, then how do we want to find the spanning tree easily? Okay, so actually we have the algorithm by using these two search, which is a depth first search and a breadth first search. So these two are different ways to get a spanning tree from the graph given. Now we look at this depth first search first. These are the steps that we will follow to find the spanning tree using this search. Okay, depth first search. So I will explain these steps using the example below here. Let's say you have a graph given like this. This is a graph, undirected. So we want to find, they say that construct the adjacency list. Adjacency list means what are the vertices connected to each other. So you need to list out all the vertices connected from 1 to 9. Which vertices connected to 1, which one connected to 2, and so on. So you put it in a table form. Okay, list out one by one of each vertex in increasing order, meaning that if you have 2 connected to 1, 5 connected to 1, and also 8 connected to 1, so we will put this in increasing order, meaning that we put 2 first, followed by 5, followed by 8. So don't put 8 first and then 2 and then 5. Okay, in increasing order. Okay. After that, they want you to use the depth first search to get a spanning tree by choosing 1 as the root. So when we draw the tree, we need to know which one is the root first. Then only we can start, isn't it? So here the question asks you to choose 1 as the root. Okay? So I will form this adjacency list first. So the first one, you have the vertex. You have 1 to 9, right? The vertex here. Vertices, list of adjacency you have here. So this one is 1, 2, 3, 4. We start with a simple example first. So the list of adjacency, just look at 1 connected to 2, 5, 8. So put it in increasing order. Okay, 2 connected to
3, 1, 9.
So 1, 3, 9. Okay, you complete the rest. Connected to which one? 2, 4, 7, right? So you have 2, 4, 7. Then 4,
3, 5.
3, 5. 5,
1, 4, 6.
1, 4, 6. 6.
5, 7, 9.
Okay, 5, 7, 9. 7,
3, 6, 8.
3, 6, 8. 8,
1, 7, 9.
1, 7, 9. And 9,
2, 6,
2, 6, 8. All the same? Okay, so these are the list of adjacency for the graph given here. Then when we want to do the depth first search by choosing the 1 as the root, so we will start from 1 here. And then go to the list of adjacency here, choose the first one which is connected to 1. So we have 2. That means you will connect the 1 to 2. I draw first, So this one is 1 to 2, right? And then 2, you come to 2 here, the vertex 2, and it is connected to the first one is 1, but the 1 just now is the root already. So we will go to the second one, which is 2 connected to 3. So we will continue here from 2 to 3. Okay? Then come to 3, vertex 3. Again, the first one is 2. So we will choose the second one, which is 4. Then you connect from 3 to 4. After that, come to 4. This one connected to 3, so 3 already here. Then you will choose the second one, which is 4 to 5. 5 to 5 connected to 6, right? Because 1 and 4 already in. 6 to
7,
7. 7 to
8,
8 to
9.
okay. Now, once we can make sure that all the vertices are in already, that means this is the minimum spanning tree. Remember just now we said undirected tree must all the vertices must be connected, right? So once you have 1 to 9 inside here, that means you already get your undirected tree by using the depth first search. Okay? So normally this type of search, the tree that you get will be long and deep, thin and long. Okay? Now this is the depth first search. Another search that we will look at is the breadth first search. So by using the same root, which is 1, so you see the next example, it is here. Breadth first search. So I will show you at the same place there, easier to refer. So this is depth first search. Now I will do breadth first search. So start with the root 1. You can see that 1 is connected to 2, 5, 8. Just now, we draw the depth first search by connecting the first vertex only. But now for the breadth first search, we will connect all. 2, 5, 8, all join together. So here you have 2, here 5, here 8. 2, 5, 8. Okay? Then you go to the next level, 2. See here you have 1, 3, 9, right? 2 connected to 1, 3, 9. So we only left 3 and 9. So here you just draw 3 and 9 from 2. And then continue to 5. So 5 you have 1, 4, 6. 1, left 4 and 6, right? Then 8 here, 1, 7, 9. So only left 7. Is it all in already? 1 to 9. All in already. Okay? Meaning that the vertices 1 to 9 already connected. And there is no cycle here. So this is a breadth first search. The 3 you get by using the breadth first search. So the breadth first search, you can see that it is short and it is wide compared to the depth first search just now. Right? That is a different algorithm that we are looking for these two. Okay, you need another example. In the notes, you only have one, right? You need extra? Yes? No need. You know? Oh, yes. Okay. I give you the graph for this one. Have you done? I give you another graph. I will draw it at the next page. we have A to I. You need to do the same like just now. Construct the list of adjacency first. So you have A, B, okay, list out one by one. So see the A here connected to
F I
Fi. B,
U H
GH, C, DH, right? D, CE, E, DI, F you have A, you have G, and you have I, right? So F connected to A, G, I. G connected to B and F. H,
E and I
B,
E
C,
I
I. And I,
A F E H
if in ascending order, we will have A, E, F,
H
H. Okay, this is the list of adjacency. Now, if let's say we choose H as the root, okay, H, start from H. So using the depth first search, can you do this first? Start from H, visit one by one, follow the list. See how is your depth first search tree. H to what? H to B, right? B to B to what? B connected to G and H, so it will go to first one G, then go to G, G connected to B and F, so B is already here, so we will go to the second one, which is F, G to F, okay, and F to
A
yes, A to
I
I to I to what?
E.
E, E to
D.
D, B, D to
C.
C.
any more? All here already, right? So this is the depth first search. How about the breadth first search? If we choose hash also, so hash will connected to BCI. All connected here. Then you go to the left hand side first, B connected to G and H. C connected to D and H. I connected to A, E, F, H. Okay, so we get this. Like this, huh? So this is a depth first search. Okay? Now for the depth first search, if let's say one of the vertex, let's say after you go to A, you cannot continue anymore. Let's say the A only have F but don't have I. So if A, you cannot continue from A anymore, what you need to do is you need to go backward to F. From A here, go backward to F and see, is there any other vertices that is not connected yet from F or not? Okay, so if let's say you have no vertices from F, then you go back to G again and check again, see any other from G or not. If yes, then you go out from G. Connect the vertex out from G until you get all are in. What we have in the example here, all are straightforward, go down until we get all the vertices, but not all the case like this. Okay, sometimes you cannot continue from one of the vertex here. So what happened if you stop halfway? You need to go backward to this F. Let's say F don't have, go back to G, G don't have, go back to B, and so on until you get which vertex is not connected yet. Then you go out from that vertex. Understand, huh? Okay. So this is what we call as depth first search. Breadth first search, no problem, you just draw all. Then you go to visit level by level. The second level here, you need to go from left first. So when you arrange this, you arrange it in alphabetical order also. This one is a B, C, I. So you arrange in alphabetical order, followed by the B first, C, and then I. Okay, so go from left to right. Okay, so this is the breadth first search and depth first search. Now, another method that we are looking at to draw this spanning tree is by using the algorithm again, which we call it as Prim's algorithm. There are two. We have two types of algorithm here, which is Prim's algorithm and Kruskal algorithm. So sometimes the graph given to you, they will have weight. Like just now, this one, the graph given, only the line from vertex 1 connected to 2, connected to 3, and so on. There is no weight given. Weight means that, let's say from 1 to 2, I give you this one is 10. This one 2 to 3 is 6, and so on. So normally this one can apply in the cost. Let's say the flight from destination A to B, take the cost of 100, and then destination 2 to 3 need the cost of 150, and so on. Okay, so that is the weight that we mean here. In the actual case, you can consider it as a cost. So what we are going to do now is we try to find the minimum weight, which means we want to find the minimum cost. Okay, so here, if there is a weight involved, we can use Prim's algorithm and Kruskal algorithm to determine the minimum spanning tree, which means the total weight that we find later on will be the minimum total weight. Okay. So for Prim's algorithm, we can do it either with weight or without weight. But for Kruskal algorithm, we will only do it with the weight graph only. Okay. So here we look at Prim's first. Now, these are all the steps for Prim's algorithm. So let's say you have the graph like this. If here A to B, the weight is 7, B to C, the weight is 8, and so on. So we can actually start with the root, any root. It doesn't matter which root you start from, the final answer will be the same. The minimum total weight, you should get the same. Okay? But sometimes, because there is alternative answer, the minimum spanning tree you get can be different, provided the minimum total weight is still the same. Okay, if you do the tutorial, you will know we have alternative answer for the minimum spanning tree, but the minimum total weight will remain unchanged. Okay, no matter which type of spanning tree you get. So, for example, we look at this graph first. How do we want to do the Prim's algorithm? First is we choose the vertex D as the starting point here. So you can see that all the weight connected to D, you have A, which is 5, B is 9, E you have 15, and F you have 6. What we need to do now is write all the weight in the vertices here. So we put it in a table form. Every step, draw a table. Okay? So you put it in a table form here. The D go to A, you have 5. This one go to B is 9. And then D go to E, you have 15. D go to F, you have 6. Okay? Now, of course, we need to find which one is the minimum. So from D to A, this is the minimum weight, right? So we will choose D to A with the weight 5. Okay? Now you see the notes you have here is different because this is a black and white only, right? Actually, this graph there is a color, so that we can differentiate which edge we want to choose. I put in different color actually, but in black and white cannot see already. So never mind, we just choose the minimum weight for this. So the first vertex we will have is D to A. This one. Okay, here. Then the next one is, because you already chose the A, so you will move the A now to the second row. In the column here, we don't have vertex A anymore. So you see in the next table, the A will be at the second row here already. And there is no more column A here. Okay? So once you move the A to the second row, now you need to do the same, where the D you just copy down from the first table just now. This one is 6. And the A you need to check again. What is the weight connected to A? So we have 7 to B. We have no more, right? So for the vertex A, it is only connected to B with the weight 7. Correct? So now in the second table here, when you want to choose the minimum weight, you'll need to choose from these two rows. Not only choose from the row A, But you need to choose from these two rows all together which one is the minimum. From these two rows here, the minimum is 6, right? So that means in the second vertex that we want to include is from D to F, which is 6. So just now we have D to A. Now we will choose D to F. This one. These two. Okay? So in the third table, you will include the F as the third row and the column here normal F already. So for the D, you still have B9, you still have E15, but no more F already. For the A, you have B, which is 7. For the F, you need to check from the graph again. F connected to E and G. So F connected to E is 8 and F connected to G is 11. Okay? Then from the 3 rows here, we will choose again which is the minimum weight. So we have this one, AB, which is 7. So in the next table, the B will be the 4th row. Okay, insert the B as the 4th row and do the same again. So now B no more in the column already. So D to E only, here 15. A no more already. F you still have E, which is 8. G you have 11. And now you need to check B. B connected to C and E, right? B to C is 8, right? Okay, so you have B to C here, which is 8. B to E is 7. Can follow until here? Yes? Can I? Okay. So out of the 4 rows here, again we need to choose the minimum, which is BE 7. So we just write out the weight. BE is 7. Now continue E as the 5th row. So we have here E, then the column only left C and G. Then the D go to E, no more already. So C and G, we only have F to G 11. F to G, and then B to C is 8. Okay, so we check E. E to G and E to C. This is 9, right? E to G is 9. E to C is 5. Okay. You also need to see other vertices. If let's say the vertices is not in the column here, you need to add in. Okay, now we don't have, so we don't need to add in anymore. Sometimes if let's say the E suddenly connected to another vertices which is not in the column here, then you need to add the column here. Understand? So here we have E to C and G only. So the minimum will be 5. EC is 5. So continue with C as the next column, next row. That means here only left G column. So F to G 11, E to G 9, and C connected to which? C connected to B and E. So no more already, right? C connected to B and E are all in already. So now left these two only. That's why the minimum will be 9. So we have EG is 9. So you can see that which vertices are chosen just now. Okay, then you just put in the graph in the spanning tree. So you just draw which vertices that you choose just now as your minimum spanning tree. So actually here have color. So what do we choose just now? This one? I draw here. Okay, first one we have AD, right? AD, DF, and then AB, BE. So your graph. So this is A, D, F, B, E. What else? E, C, E, G. E, C, E, G. So we have this. Then the weight, you can write down 5. DF is what? DF 6. BE also 7, EG 9, EC you have 8, EC is 5. So we follow the original graph to draw the spanning tree. Okay? This one, the spanning tree you get from the original graph. Which vertex you choose, then you draw it. So what is the total minimum weight here? Huh? What is the minimum total weight?
Thirty-nine.
39, Okay, so this is using the step algorithm for Prim's algorithm. Any question?
How about have the same weight?
If the weight is the same, right, you can choose either one. No? So let's say now the DF, the EF, see which one. Okay, now let's say the EC is 5. At the same time, your BC also 5, for example. Then you can choose either one. If you choose EC, right, or BC, you need to make sure that the one that you choose must have no cycle. If either one of them, the weight are the same, but when you choose, it will form a cycle with the previous vertices that you have chosen, then you cannot choose that also. Like this one, BC is fine, not a cycle, right? Let's say you already choose BC, you already choose BE. Now can you still choose CE or not? Of course cannot, right? Because if you already have BC and BE, you still choose CE, means that it will form a cycle already. And just now we already defined that if it is a tree, it cannot have a cycle, right? So you need to choose the one with the minimum weight and without a cycle. Okay, but if both also will not form a cycle, then it will have alternative minimum spanning tree. No problem. But the weight are still the same. Minimum total weight will still be 39. Understand? Okay, maybe you draw the one and your friend one will be different tree lah, but the weight are still the same. So this is the Prim's algorithm lah. Okay, you need a break now? Okay, take a